Welcome to a course on sequence and series. In this lecture, we are going to see some properties, that is the theorems based on the convergent sequences. You may see the theorem statement now. In this, it is given that a Pn is some sequence in any metric space X, right? So with that, what are we going to prove? The sequence converges in X, that is, it has some limit P in X to which it converges. It is going to happen if and only if every neighborhood of P contains all but finitely many points of the sequence. It means what? It will have almost all the points of the sequence excluding some points in the sequence, which means we are just going to neglect only a finite number of points in the sequence and all other terms in the sequence will be there in the neighborhood. That is what we are going to prove first. Now let us get into the proof formally. Okay, here what are we going to do? We are going to do this in two cases. I mean, two ways we have to do. First, let us assume that Pn converges to P. By the definition of a convergent sequence, what do we have? By definition, we have there exists n, okay, there exists some n which is a positive quantity, right? Okay, there exists some stage n for every epsilon greater than 0 such that what is going to happen? D of Pn comma P is less than epsilon whenever n is bigger than or equals n. When this is going to be the case, this is going to happen. Now, you see, here we have fixed some n, right? So till that n, you do not know what is going to happen, but after this n, all those points are to be collected in this. Okay. Now, let us consider a neighborhood of P with radius epsilon. Okay, we may choose any radius, right? Let us fix this epsilon to be my radius. Then neighborhood of P with this radius is going to be the collection of points in the metric space such that D of P comma Q less than epsilon, right? So what are the, here you may see that if you have this to be equation 1 and this to be equation 2, from 1 and 2 you may see that your Pn is a member of this neighborhood for all n bigger than or equals n. After this stage, all the terms in this sequence is being a member of this neighborhood. This is what we needed to prove, right? So we have done the first way. Conversely, what is going to happen? We need to assume some neighborhood of P. Okay, let me call that to be V. Okay, contains all but finitely many points of Pn. So this is the hypothesis that we are taking. By this hypothesis, what are we meaning? Okay, here let me choose the radius to be epsilon. It is just the name. Okay, you may take it R as well, right? Here I am just taking the radius to be epsilon. Okay, then what is going to happen? V is going to collect the points in X such that D of P comma Q less than epsilon. This is my V, right? In this V, excluding finite number of points in this sequence, I am having all other points to be present in this neighborhood. Okay, so for this V, there exists some n. Okay, there exists some n, a positive integer n, okay, such that what is going to happen? This Pn is a member of V for this thing, right? Here, if you notice this thing, these points are present in this V. This is what we are saying. We are not saying only these points are present in V. These points are present in V. There may be many other points as well, right? Now, if you just look at these things, okay, now forget about this thing, just look at these things. These points will satisfy this condition, right? So, what you are having? You are having that d of p comma pn is less than epsilon for n bigger than or equals n. And this proves what? This proves Pn converges to P, right? In the second part of this theorem, it tells you that a sequence, if it is convergent, a sequence is convergent if and only if it has a unique limit point. That is, if we are taking two things, right? P and P prime are 2 points to which the sequence converges means those 2 points will have to be same, which means a convergent sequence will have unique limit point. That is what we are going to prove here, right? So let us assume that Pn converges to P and Pn converges to P prime as well. What should we prove? We have to prove this P and P prime are same. Okay. This implies Pn converges to P implies there exists. Okay. Let me put it in another way. Okay. What am I taking is that there exists for epsilon greater than 0. This epsilon is what? It is a very small quantity, any negligible quantity, right? So let me take epsilon by 2 as well. For epsilon by 2 greater than 0, there exists a positive integer. Okay, we may mention this to be positive integer because it is positive integer, right? There exists n such that d of Pn comma P less than epsilon by 2 for n bigger than or equals n. Okay, similarly, you have what? This Pn converges to P prime tells you d of Pn comma P prime less than epsilon by 2 for n bigger than or equals n. Now, consider d of P comma P prime. Using the triangle inequality, since d is metric, we may write this to be d of P comma Pn plus d of Pn comma P prime, right? And what is going to happen? Using the symmetry, this is epsilon, this is less than epsilon by 2 plus this is also less than epsilon by 2. Together we are going to get epsilon. And this is true only for n bigger than or equals n. So this tells you your d of P comma P prime is less than epsilon. What is this epsilon? This is a very small quantity. This is almost zero kind of a thing, and you are saying the distance between these 2 points is of this sort. This tells you what? This tells you your P and P prime must be unique, right? So this completes the proof of this part, right? In the third part, what are we going to do? In the third part, we are going to prove if a sequence converges, then the sequence has to be a bounded sequence, right? And in this part, that is in the second part of this theorem, we have proved convergent sequence will have a unique limit point. This is what we have proved, right? So sometimes a limit point need not even though it has a unique limit point, the sequence may not be convergent, because if the limit point is infinite, we cannot come to a conclusion that it is convergent, right? So we have seen some examples that will give you the idea of what the theorem is all about. You have to remember that if a sequence is convergent, then it will have a unique limit point. Okay, and in the third part of this theorem, what we are going to prove is that convergent sequence are bounded. Bounded sequence need not be convergent, right? For which I can give you a counter example at the end as well. Let us now prove the third part. Okay, we are taking the assumption that Pn converges to P. If Pn converges to P, what is going to happen? There exists epsilon for every epsilon greater than 0, there exists what? There exists a positive integer n such that d of Pn comma P less than epsilon for n bigger than or equals n. Right? Now, for simplicity purpose, I am choosing epsilon to be 1. You may choose any epsilon that you want. Okay? It need not be even 1. You may choose that to be 2, 0.5, 0.75. But it has to be some positive value, right? Like that, you may choose any epsilon, and after the stage, your distance is less than epsilon, which means till this distance, that is till d of Pn comma P, what is going to happen that you don't know. This is the meaning of this, right? After this is going to be lesser than epsilon. Now, what we are going to do is that we are going to take R to be the maximum of d of P comma P1. Using the symmetry, I am writing this way. P comma P2, and it goes till d of P comma Pn and this epsilon value. I am taking the maximum of these values to be R, and you may notice that these are all positive finite quantities. Therefore, the maximum among this has to be some finite quantity, right? A finite positive quantity. Whatever may be the value that you choose here, it doesn't bother when we take maximum. Okay? Now, if you take this way, what is going to happen? You will have the requirements. That is, your d of Pn comma P is less than or equals R for all n. Right? So this is going to happen. If this is going to happen, what? This means what? This means the sequence Pn is bounded. In the fourth part of this theorem, what we are going to do is that we are taking a subset in a metric space, and some point is a limit point of that subset, right? If we take a limit point of any subset, we can identify some sequence in the subset which converges to that limit point. Till now, we have a sequence. We are talking about the convergence of the sequence. If it is convergent, what is going to happen? All these things we have done. Here, in this, what should we do? We have to construct a sequence which converges to the point that we have. Right? Here, what is given that let E be a subset of X and P be a limit point of E. Right? P is taken to be a limit point of E. Now, by the definition of limit point, what do we have? There exists at least one point of E in the neighborhood, whatever may be the neighborhood that we take. Okay, or in neighborhood. Let us simply write in neighborhood other than this Okay, this is what we have from the definition of a limit point, right? Now, for whatever may be the radius that I choose, right? So for n bigger than 1 or bigger than or equals 1, let me choose my r to be 1 upon n. So for each n, I can identify some point, and that point I am going to name it as Pn. Okay. So for n bigger than or equal to 1, let me choose r to be 1 upon n. So for every n, there is a element Pn in E such that what is happening? D of Pn comma P is less than 1 by n. This is the radius that I am choosing, for which I can identify some point in E such that this is happening. Okay. Now what am I going to do is that I may take any epsilon greater than 0. Okay. I am taking an epsilon greater than 0 and I have 1. Supposing I have 1. Okay. Using Archimedean property, I can identify an integer such that what is happening? This n times of this epsilon has to be greater than 1. I may identify such things. Now, for n bigger than or equals n, what should I have? 1 upon n less than or equals 1 upon big N. Okay. Now consider d of Pn comma P after this stage. Okay. This is going to be what? This is going to be less than 1 upon n. Now I am talking these things after this stage, which means this 1 upon n is less than or equals 1 upon n, and from this what do you get? This implies your epsilon is bigger than 1 upon n, which means your 1 upon n is less than epsilon. So this is less than epsilon. So for every epsilon, you are able to identify some n such that this is happening. Okay, this tells you what? Your Pn, sequence Pn converges to P. Right? We have come to the end of this lecture. Thank you.